In this video, we are going to have the proof of Wedderburn's theorem. It states that a finite division ring is necessarily a commutative field. So to prove the theorem, we are going to have certain concepts. They are given as a fact 1, fact 2 and the definition of cyclotomic polynomial. So we are going to have the first proof of Wedderburn's theorem. That is with the help of number theoretical concept that we will be establishing the first proof. So first fact, this is known from finite fields, that if V is a vector space of dimension n over a finite field with q elements, then V has q power n elements. So for that, suppose we consider V to be a finite dimensional vector space over a field F of dimension 3, and F has it's a finite field with 2 elements A, then we will establish that V has 2 cubed elements. Now V being of dimension 3, it will have basis elements, 3 basis elements, V1, V2, V3, let them be V1, V2, V3. Then capital V being the linear combination, we can have capital V as this, where alphas range over capital F. Capital F has only 2 elements, 0 and 1. So from this table that we can see that these would be the elements of capital V. Your alphas can be zeros or all of them can be ones, or 1 is 1, the rest 0. So that means these 3 combinations that we have, and 2 are ones, the rest is 0, there is a third one is 0. So these 3 combinations we have. So when we substitute the values for alphas here, we list out the elements of capital V as this. So this V has 2 cubed elements. So this is in the case of V vector space, which is of dimension n. Now in particular, if we consider K to be a ring containing a field Z, so how can a ring has a field Z? That Z is nothing but the center of that K, those elements which commute with the elements of all the elements of K. So this would be a field, and K is a ring containing a field Z. Let this Z have q elements. Then by the above concept, we have K consisting of q power n elements. So here, even though we mentioned that dimension of K is n, this is regarded as a vector space, because for vector space V should be a abelian group under addition, and K is always being a ring is always a abelian group under addition. And when we take the element, this is actually a subcollection of capital K. So automatically that scalar multiplication axioms will also be true. So K can be definitely regarded as a vector space over that Z. So if that has, so we can now regard that to be a finite dimensional vector space with dimension n, means by the above discussion we can have K with q power n elements. Now the next factor is, if t is greater than 1, if that is an integer, then and you are given this t power m minus 1 divides t power n minus 1, then what is the relation between this m and n? This m should divide n. So that is what is established here. Suppose we have n to be n is, m does not divide n, then you have that n by Euclidean algorithm, given integers n and m, there exist integers l and s, such that n is equal to ml plus s, with either 0 less than s less than m, or s is equal to 0. We are going to claim that this s is only 0. Suppose we assume this, then we have to get a contradiction. So now suppose we have this to be true, where s is less than m. If s is less than m, t power s will be less than t power m. So t power s minus 1 will be less than t power m minus 1. We shall name this as statement B. Now you consider t power n minus 1. This n is replaced by this ml plus s, ml plus s. And then you add and subtract t power s. So you get this step. So t power n minus 1 is rewritten in this way. Now we are given that t power m minus 1 divides t power n minus 1. So this t power m minus 1 divides this, and this is known to us. T power m minus 1 will always divide t power ml minus 1. Say for example, if we consider x square minus 1, that should divide x power, this m is taken as 2, means here 2 into 2 or 2 into 3, whatever that you consider. Okay, then multiple of 2. Here 2 means here multiple of 2. When we consider, naturally this one will divide this. So because of these two, we have t power n minus 1 being divisible by this, and this is also divisible by the t power m minus 1. Our t power s minus 1 should be divisible by this. So t power m minus 1 divides this, which contradicts p. In this we have said that this is greater and this is lesser, and here we are getting the other way around. So that contradicts p. So that contradiction tells us that this s can only be 0. Therefore n equals ml, or in other words m divides n. So whenever we have this to be true with t greater than 1 to be an integer, then your m must divide n. This we shall name as fact 2. Now we will have the definition of cyclotomic polynomial. For that we consider the polynomial x power n minus 1 over the field of complex numbers. Now the nth roots of 1, if we name them as 1 lambda, lambda square and so on, lambda power n minus 1, then we can write this x power n minus 1 as. So actually here this not directly lambda, lambda square that we have taken, but lambda, lambda 1, lambda 2, like that when we consider x power n minus 1 as the product x minus lambda, we shall name this as statement A, where this product is taken over all lambda that satisfies this. Now the name given to this lambda, say either you denote it as lambda or theta, whatever it is. So here what is the name given to that? So that is explained here. A complex number theta is said to be a primitive nth root of unity, that is 1, if theta power n is 1. Theta power n is 1. But theta power m is not equal to 1 for any positive integer m less than n. Now the nth roots of 1, okay, then that collection form a cyclic group under multiplication of complex numbers. So that is true fact from our group theory. Now any cyclic generator of this group is called a primitive nth root of 1. So generators, it will have, being a cyclic group, it will have generators. It's not that all of them will be generators. Those generators are called the primitive nth root of 1. Now if we denote this phi suffix n of x as the product x minus theta, where this product is taken over all the primitive, it is not n, it is m, all the primitive nth roots of unity, then this polynomial is called cyclotomic polynomial. So this polynomial, which is named as 1, is called the cyclotomic polynomial. Now we consider we are going to have we are going to group the terms in the product in such a way that this theta, okay, those thetas whose order is d, where d is less than n. So for that this argument is given. Consider the polynomial x power n minus 1. Then the nth roots of 1 are given by e power 2 pi I k by n, which we denote as theta suffix k, where your k range from 0 to n minus 1. So this comes from your trigonometry solving nth degree equation. So all the roots we have mentioned, some of them will be real. Real means you will have 1 and minus 1, the rest will be definitely complex numbers. Now some of the roots satisfy theta power d equal to 1 for d less than n. For n it is definitely true. Theta power n is 1. But what we say here is when we have n, and especially when n is an even number, for d less than n, we have theta power d to be 1. So, for your root theta, if we denote d to be the least positive exponent with theta power d equal to 1, that is, d is the order of theta, where theta is a member of the group of all nth roots of 1, whose order is n. Then, by corollary to Lagrange's theorem, we must have our d dividing n. See, here, suppose I have n to be 6. Then there will be roots of x power 6 minus 1 whose orders are either 3 or 2. Of course, we will have identity element, namely 1 with order 1, and definitely we can have elements whose order is 6. But what we try to mention here is there are also roots of this whose orders are either 3 or 2. So, for your root theta, if we denote d to be the least positive exponent with theta power d equal to 1, that is, d is the order of theta, where theta is the member of all nth roots of 1, then the relation is by Lagrange's theorem, we have d to be less than n, d to be divisor of n. So, we collect all the roots. So, when consider this, if we consider this, then it will divide 6. That is one thing. And we will also have such numbers. So, the relation between those numbers and n is naturally they should be divisors of n. Without knowing this also, when you consider, you list out those members whose order is some d. You can definitely see that the d to be a divisor of n. That is what is mentioned here. Now we collect all the roots of x power n minus 1 of order d together, right? And then take that collection. So x minus theta, the product of this is denoted as phi d of x, where theta is order of d. Those thetas with order d, they are collected. And that collection, that product, is named as phi suffix d of x. So this is a notation that is introduced. Now, since every root has some order d, we have x power n minus 1, which is written in this way, d dividing n. Now, in this, what we do is d divides n. In that case, even my d can be n. So that is taken separately. So the rest will be the product in which d divides n, but d is not equal to n. So this is taken out and the rest are written. So from here what we conclude is phi n of x is x power n minus 1. We are taking this to the other side. So divided by this. D divides n, but d is not equal to n. So thus x power n minus 1 you have. Now you can consider cross multiplying by taking this as g of x. So g of x is a monic polynomial with integer coefficients for d dividing n, d not equal to n. So that is explained here. And so from here when we denote this by g of x, what we have is phi n of x to be x power n minus 1 by g of x. Now here we are listing out the cyclotomic polynomials for n equal to 1, 2, 3 up to 5. So when you consider phi 1 of x, you have that to be just x minus 1. Phi 1 of x is just from here. You have phi 1 of x to be just this, because d equals 1, d divides n. In this case we have just 1 only. So x minus 1. Now for n equal to 2, we have in the product, then the divisor of 2 is just 1 and 2, and here in the denominator when you consider 2 should not come. So you have just phi 1 of x, and in the numerator n is 2, so you have x square minus 1 by this. but this is computed already, and so you have phi 2 of x to be x plus 1. Now we will concentrate on n equal to 3. The divisors of this are just 1 and 3. The divisors of this are 1 and 3, but when we consider in the denominator, d should not be equal to 1. So 3 is should not come here. So only 1, that is phi 1 of x. So here n is 3, in this case n is 3, so x cube minus 1, phi 1 of x is x minus 1, so you have this. And this on division by x minus 1, we know that that is given by x square plus x plus 1. Now when n equals 4, the divisors of this are 1 and 2. So in the denominator, and 2 is not equal to 4, so in the denominator we should have the product with phi 1 of x and phi 2 of x. And the numerator that we have as such by replacing n by 4, this is what we have. And this phi 1 of x we have already computed, phi 2 of x also we have got, and therefore this gives us x square plus 1. And when n equals 5, again 1 and 5 are the only divisors. So we have only one factor in the denominator, and this one gives us this. So by induction we may assume that phi d of x is a monic polynomial with integer coefficients. The coefficients are all integers. Monic means coefficient of highest power is 1. What is that we have between the relation between d and n? D divides n, d not equal to n. So that is what is mentioned here. X power n minus 1, which is this, where g of x, this one, where this g of x is a monic polynomial with integer coefficients for d dividing n, d not equal to n. So you have phi n of x, just cross multiply, you have this. Now we claim that if d divides n and d not equal to n, then phi n of x must divide this term, x power n minus 1 by x power d minus 1. Now you consider x power d minus 1. This is just the definition of that is from 2 that we are writing it. 2 is this, x power n minus 1 by definition is nothing but this. So when we consider this, we can also write this one as phi k, k divides n and k divides d, right? The relation, first actually you have this to be phi k of x. In this case, as per this, it is enough we write this, k dividing n need not be written. But in the next case that we need to have, that is why here it is mentioned. As such, here with the help of this, when we write, there is no need to mention about this n at all. K and d are only involved. So as per 2, this need not be written. But the next case, when we consider x power n minus 1, we need it. So by mistake, that is written here. Now, when we consider x power n minus 1, we have that to be corresponding to d equal to n. See, x power n minus 1 is this. Corresponding to d equal to n, we have taken phi n of x out. And then d dividing n cases, that we know, that is denoted in this way. So x power d minus 1 is also removed. Now in the product, what remains is phi k of x, that product, but k divides n. Here k does not divide d, right? So the one with that concept that is taken out. So the remaining should be k not dividing d only. So from here we have x power n minus 1. We are taking this to the other side. What is left is this and this one. This, if it is taken as f of x, this is what we have. So from here it is obvious that phi n of x divides this. That is our claim. So this is our claim, and we name this as 3 and this as 4. We will be making use of them later. Now starts the main proof, which is the first proof of Wedderburn's theorem using the number theoretical concept. Now let K be a finite division ring, that's given to us, and Z be its center. Then that is those elements of K which commute with all the elements of K. Now let Z have Q elements. This is finite, means this will also be finite. We shall take the number of elements in this to be say Q. Now by fact 1, K should have Q power n elements. Now we claim that Z is K. So that is what we want actually. When Z is K, that is when n is 1. If n is 1, then we will have our Z to be K. Now suppose n is greater than 1. Suppose n is greater than 1, then we are going to have a contradiction. So once we show that Z equals K, K has those, Z has those elements which commute with all the elements of K. So once you have K to be Z, then all the elements of K will commute with all the elements of K, and therefore K becomes a commutative division ring, and therefore it has to be a field. So if A belongs to K, we will consider an element A in K. Then for that element we can find the normalizer of A, all those elements which commute with only A. Now we know already that the relation between the center and normalizer of an element is the center is properly contained in n of A, and n of A is a subdivision ring of K. It is easy to establish that n of A is a subdivision ring of K. So by corollary to Lagrange's theorem, this n, Lagrange's theorem, order of n of A must be equal to Q power n of A. So why we say this is is by Lagrange's theorem, being a subgroup of K, it should divide, and the number of elements present in K is Q power n, we have said. So order of n of A being a divisor of Q power n of A, remember that Q is a prime number. Q is a finite field we have, so Q must be prime. So order of n of A is a number dividing Q power n, where Q is a prime number. So it should be of the form Q power some integer. That integer we are taking it as n of A. Now what is the relation between this n of A and n? N of A must divide n. N of A must divide n. Now since the non-zero elements of n of A form a subgroup of order Q power n of A minus 1, non-zero elements. With 0 it is Q power n of A. Non-zero means we are removing 0, so minus 1 that you have. Of the group of non-zero elements under multiplication of K, non-zero again, Q has already Q power n elements, so you are removing 0, so that means these Q power n minus 1 elements will only be there. So by Lagrange's theorem, this must divide this. So this implies already by fact 2, we have got fact 2 is this, t is greater than 1 is an integer with t power m minus 1 dividing this, and this we have n of A to be greater than 1, so we can apply this. So from fact 2 that you get n of A dividing n. So that proves our claim that n of A divides n. Now in the group of non-zero elements of K, we can have this relation A is conjugate to B if A is x inverse B x for some x not equal to 0 in K. Now the number of elements in K conjugate to A, see the 0 element is removed, so we are applying that theorem which is given in another counting principle, so to K star only. So you have order of K star by order of n of A the whole star. That is 0 is removed from them, and this is Q power n minus 1 and this is Q power n of A minus 1. Now from the class equation we have this step, that is this one denotes those elements which are in Z, 0 is removed, so you have this. So order of, and we have already said that Z has Q elements, so Z star will have Q minus 1 elements, and order of K is Q power n, order of K star will be Q power n minus 1. So this is written and this is written, and this is Q power n minus 1 by Q power n of A, because this is this. By that class equation, just substituting that over here, we have this. and in this n of a divides n, but n of a not equal to Cn. Now from 3, what is 3? From 3 we have that this we already established. In 3 we have this is what 3 is, phi n of x dividing x power n minus 1 by x power d minus 1. So we make use of that in this case. So you have this. So by that you have phi n of q to be a divisor of q power n minus 1 by q power n of a minus 1, as n of a divides n. Now from 4 what we have is phi of n of q dividing q power n minus 1. Phi of nq divides q power n minus 1. Again, what is 4? Here phi of n of x divides x power n minus 1. So that is used here. So from 4 that you have this, and using this in phi, this is what phi is. That is class equation we had, so from that you have this. So using this in phi, we get phi n of q dividing q minus 1. So name that as 6. See, phi n of q divides this, phi n of q divides this from here. So this is divisible by phi n of q, this is divisible by phi n of q, and so this is divisible by phi n of q. Name that as equation 6. Now phi n of q, already at the beginning we have mentioned, that x power n minus 1 is given by product q minus, x minus lambda. Here in the place of x you have q. So you have that x over there is, we can have it as their polynomial in that sense that was discussed here. It's a number. So q minus lambda from the first one that you have, very first statement what we gave. So from that you have this. Now name this as 7. Now since lambda is one of the roots, see, lambdas are all roots of the given x power n equal to 1, that is the nth roots of 1, that accepting 1 you have that the rest to be complex numbers. So you have x power n minus 1 will having this as a root. You are considering one root, a plus ib, and n is greater than 1, so lambda cannot be 1. Now this implies that a is less than 1. The reason is when we consider 1, which is mod lambda the whole square, we have this one because lambda is a plus ib, you have this to be a square plus b square. So when a square plus b square is 1, naturally your a should be less than 1. Now we consider modulus of q minus lambda the whole square. Replace lambda by a plus ib. So you have this. So real part square plus imaginary part square, and this is what you have, q square minus 2aq. A square plus b square you will have, but a square plus b square is 1. So you have this step. And because your a is less than 1, minus a will be greater than minus 1. So you have this step. But this is nothing but q minus 1 the whole square. So modulus of q minus lambda the whole square is strictly greater than q minus 1 the whole square. And therefore modulus of q minus lambda is greater than q minus 1. So from 7 that we have your 7 is this, phi n of q is equal to this. So from that we have this the modulus of phi n of q to be greater than q minus 1. You have this to be the product of all this. So when you consider the modulus of this, one of the any random lambda that is considered excepting 1. So in that case, each one being greater than this q minus 1, you will definitely have that to be greater more than that, but definitely greater than q minus 1. So from 6 and 8, here we have sixth statement was this: phi n of q divides q minus 1. But here phi n of q is greater than q minus 1 that we get. So these two are contradicting. This is a number which is greater than q minus 1. But the greater value divides the lesser value. That's not possible. So from 6 and 8, we are getting a contradiction. So you have, at the beginning we said that let n be greater than 1. Okay, instead of n equal to n. So that conclusion, that assumption is wrong. So we conclude that n should be 1. When n is 1, you have your k to be equal to z. That was our claim at the beginning. So that proves our theorem. So this is the first proof of Wedderburn's theorem using number theory concept. Thank you.